Good afternoon. I am Choi Pui Tong, a graduate student of Baptist呂明才Secondary School. Today I am glad to have a chance here to present my research about the centers of tetrahedra. In secondary school, we have learned about the centers of triangles: the circumcenter, the incenter, the centroid, and the orthocenter. These four centers exist for all triangles. Then how about tetrahedra? Do these kind of centers exist for tetrahedra? And this question begins our research. First, we would like to take a look at two special cases. Then we will go into the general case. We will start from the centers of triangles and to the centers of tetrahedra. And also, we will take a look at some properties of the centers of tetrahedra. Let's start with two special cases. The first case is regular tetrahedra, and the second one is the tetrahedra with three pairwise orthogonal isosceles triangular faces. We found that for these two cases, all four centers exist. And these two cases motivate us to carry on our study. Then we carry on our study to the general situation. We try to prove the case about triangles first and get some motivations, and then we make use of some main ideas in the proofs to prove the case about tetrahedra. Let us start with circumcenter. The circumcenter of a tetrahedron is the center of its circumsphere. And we wonder, do all tetrahedra have circumcenters? Well, to answer this question, let us take a look at the case about triangles first. Well, the main idea of the proof is that we construct two lines, and each line is equidistant from two of the vertices. And we prove that these two lines will intersect at one point. Then we tackle the case about tetrahedra. Again, we construct two lines, and each of them is equidistant from three of the vertices. And then we prove that these two lines are actually coplanar, so they will intersect at one point. And these prove the existence of circumcenter for all tetrahedron. Then we come to incenter. The incenter of a tetrahedron is the center of its insphere. And our question is, do all tetrahedra have incenters? Again, let us first take a look at the case about triangles first. Well, the main idea of this proof is that we consider a triangle with its orthocenter, with its circumcenter O, and then we construct a larger triangle which have O as its incenter. And we prove that these two triangles are actually similar. And so, the existence of incenter follows the existence of circumcenter for all triangles. Then we consider the case about tetrahedron. We consider a tetrahedron and it is with circumcenter O, and then we construct a larger tetrahedron which have O as its incenter. And we prove that these two tetrahedra are actually similar. So the existence of incenter follows the existence of circumcenters for all tetrahedra. Then we go to orthocenter. The orthocenter of a tetrahedron is actually the intersection of its four attitudes. And we wonder, do all tetrahedra have orthocenters? And the answer is no. We just find a counterexample. In this counterexample, the attitude drawn from A to plane BCD and the attitude drawn from C to plane ABD obviously do not intersect each other. So orthocenter do not exist for this tetrahedron. However, we are still interested in finding out which types of tetrahedra have orthocenters. And motivated by the two special cases we considered at the beginning, we then found that the tetrahedra having three pairwise orthogonal faces actually have orthocenter. And the orthocenter is exactly at one of its vertices. And then we try to take a look at the case about the orthocenter for triangles. And the main idea of the proof is that we consider a triangle with its three attitudes. And we construct a larger triangle which is similar to the previous one. And the three attitudes of the inner triangle is actually the three perpendicular bisectors of the outer triangle. And we know that the three perpendicular bisectors of the outer triangle should intersect as the circumcenter of the outer triangle. And so the orthocenter exists for all triangles. And we follow this proof to the case about tetrahedra. We consider a tetrahedron, and by similar way, we construct a larger tetrahedron, which is similar to the previous one. And then we found that the orthocenter of the tetrahedron exists if and only if the four normals passing through the centroid of the faces of the outer tetrahedron are actually concurrent. Then, we found that the four normals are concurrent if and only if the tetrahedron is actually rotationally symmetric about one of its attitudes. Well, the proof is divided into two parts. In the first part, we prove that D prime is actually one of its attitudes. And in the second part, we prove that A prime, B prime, C prime is actually a regular triangle. And so we identify that only two types of tetrahedra have orthocenter, and these are the two types. Then we come to the centroid. The centroid, we want to prove that the four lines is each drawn from a vertex of a tetrahedron to the centroid of its opposite triangular faces will intersect at one point. And the proof is as follows. We divide it into two parts. In the first part, we prove that every two of the four lines will intersect at one point. It is because every two of them are actually coplanar and they are not parallel to each other. And then we prove that these four lines will actually intersect at exactly one point. We proved it by contradiction. First, we assume that three of them do not intersect at one point. And then the fourth line cannot intersect all these three lines. And so a contradiction is occurred. Then we conclude that centroid exists for all tetrahedra. Now, we come to some properties of circumcenters. As we know, the circumcenter for a triangle is the intersection of its three perpendicular bisectors. And then we find that there is actually one similar property of it for the circumcenter of tetrahedron, which is the circumcenter of a tetrahedron is the intersection of its four normals drawn from the circumcenters of the four triangular faces of the tetrahedron. And then, for the incenter, we know that the incenter of a triangle is actually the intersection of its three angle bisectors. But angles is not well defined for tetrahedron. We then observe that an angle bisector for a vertex of a triangle is actually a line equidistant from two of its edges. And we find that every point on the line passing through the vertex and the incenter of a tetrahedron is also equidistant from three of its planes. So we define the equidistant line of a vertex of a tetrahedron. And we conclude that the incenter of a tetrahedron is actually the intersection of its four equidistant lines. Then we come to centroid. We know that for triangles, centroid divides its medians in a ratio 2:1. And naturally, there is a similar property of it for the centroid of the tetrahedron. But this time, the ratio is 3:1 instead of 2:1. And also, we found that we can actually represent the coordinate of the centroid of a tetrahedron by the arithmetic mean of the coordinates of the four vertices of the tetrahedron, which is similar to the property we know for a triangle. And we come to the conclusion. Circumcenter, incenter, and centroid exist for all tetrahedra. We prove this by making use of the main ideas in the proofs for the centers of triangles. Also, we found that orthocenter exists for two types of tetrahedra. The first one is the tetrahedra with three pairwise orthogonal faces, and the second one is tetrahedra which are rotationally symmetric about one of its attitudes. Also, we found some beautiful relationship between centers of triangles and centers of tetrahedra. We found that circumcenter exists actually implies incenter exists, and there are some similar properties between the centers of triangles and the centers of tetrahedra. And we actually have some ideas for further study. We asked several questions. The first question is, can other properties in plane geometry also be extended to the 3 dimension? And the second question is, how about higher dimensional case of this problem? For example, did there exist the centers of a pentatope? And I believe that in finding out the answer of these 2 problems, we will definitely have a chance to explore the beauty of geometry. And that's the end of our presentation. Thank you.